Okay. So the next part, again, I said I would do one proof at maximum. There are proofs for where these come from, just like I proved to you the derivative of sine is cosine. You're capable of understanding them. You may want to look in your textbook. If you're the kind of person who has to know, I need to understand why, you're going to want to look at those proofs. But there's no other easy way around this. You do need to know the remaining 4 trig functions and their derivatives. So these are the 4 of them on the board here, and you'll need to know these 4, and there are no formula sheets for your AP exam. So one trick, I've written it in one way that I use to help me remember. One trick is that the way I've written it out, so for example, when tangent goes to secant squared, and secant is secant tangent, on the other side, I get cosecant, cosecant, just like I get secant, secant. I get cotangent, like I have cotangent, and tangent, like I have tangent here. So they do kind of parallel up because these things are loosely related by those fractions in the trig ratios. Another thing is, on this side, they're both negatives. So however you digest the information, unfortunately, those are some other things you're responsible to know without a formula sheet. You'll be expected to know those derivatives. You won't have to prove them, but you will have to know them. And again, it's not an issue usually by the end of the year when you've been doing it all semester. But at this point, I understand it's a little bit, there's a lot to digest, and I'll do my best not to put all 6 or 10 or whatever it is rules on your quiz and test. I'll try to make it manageable while we're still practicing. So here's what I'd like you to try, and I'm just going to emphasize as try, okay? So first of all, I want you to take 1 minute to look at your trig rules for derivatives. Just take a minute, look at them, try to memorize, try to think of how you could remember them, think of a strategy. Then I want you to put your textbook over top of them and try to do the next 2 without using your little cheat sheet there, okay? So just try it, just simulate it, okay? 1 minute to try to remember, then cover it up. I'll tell you when that minute's up. We'll cover them with the textbook. So hands up, could you do it without looking at your cheat sheet? Yeah, that's about what I figured. It's okay, again, we're going to keep practicing. But for our first piece, there's no product or quotient rule. It's just to try using the derivative. It should be 1 minus secant squared x. And in this one, there is a product rule. So it'll be derivative of one piece plus the derivative of the other. And for secant x, this will be tangent squared x. So one thing you should note too, your textbook may have written this in as negative tangent squared x. That's a possibility. Why do you think your textbook may have that answer? You said the right word. What did you mean by trig? Would it help if I gave you another letter?
Yeah.
I? Yeah, there you go. Okay. So trig identities, you may end up with seeing a different answer even though you're so convinced that you have it correct. So for example, here's y equals 1 minus secant x squared. Put it in your graphing calculator. There's the picture. Now say, okay, if I'm correct and the textbook is also correct, the graphs should look the same. So here's negative tan squared. Same pictures. That's enough probably to convince you that, okay, the textbook has done some other trig identities, and that's okay. It just means you're both correct. Okay, so if you get confused by an answer when you're checking over your homework, you may want to check that they haven't done some trig identities. So speaking of which, it's possible that we find a derivative like this one. Some of you may prefer this because you may say, oh yeah, well Mr. Joyce, I know the derivatives for sine and cosine. Those ones are easy to remember, so I'd rather work with this fraction. Some of you might say, well, I don't really like doing the quotient rule. This would be much better to work with. These are actually equivalent because the first piece here I could rewrite as 1 over sine x minus cosine x over sine x. So that would be the cosecant of x, take away the cotangent of x. Okay, so keep in mind when you're working with trig, you have that freedom still of using your trig identities to help you find a derivative. Okay. In this situation, if I was just to go directly like I have on the right-hand side, okay, the derivative for cosecant is negative cosecant x times cotangent x. And I'm going to take away, it'll be negative, let's see, who knows the cotangent? Anybody without looking at your book? Do you remember? Yeah, cosecant squared, good. So that would become a plus sign, obviously. So, okay. So that's all we're going to take the time to talk about quotient and product rules today. The last idea is, it sounds really hard, but it's actually really easy. And it has a lot of applications, one of which we'll talk about here. And they're what we call higher derivatives. So first of all, you've been taking a derivative. But now a higher derivative, what that means is the derivative of a derivative. And that's where everybody goes, oh my god, I'm scared. I thought derivatives were bad enough. I'm going to go see my counselor after this and transfer out. But trust me, this is actually really simple. We'll do one right now. Okay? So for example, here's a function. What's its derivative? 2x, okay, simple enough. Here's a function. What's its derivative? Okay, so you've just taken a derivative of a derivative. Okay, what's its derivative? Good. What's its derivative? 0, yeah, it's still a constant. Okay, so what's its derivative? You could just keep going, right? You can always take the derivative, well, usually you can take the derivative of a derivative, and that's what we call a higher derivative. So why would we want to do this? Well, oftentimes we're interested in how the rate of change changes. One major application in calculus that we'll look at is stuff you see in physics, like distance and things like that. Those of you who are going on to business, there's another major application of in finance. In the options world of, people know what I'm talking about when I say like stock options? Really? Business ed has failed us in this school? Anyways, the models they use for stock options, the people in business are always interested in how fast they are going to be changing to adjust their portfolios and things like that. So they look at the rate of change in the money they're interested in, and they're also interested in how fast will the rate of change happen, because you don't want to be sitting on something that might require you to move, say, like $1 billion in 3 minutes. That's a pretty fast rate of change. You probably can't do that, right? They are also interested in this stuff in options. So it won a Nobel Prize in the 70s if you look it up on Google. But for our class, the primary one we're going to look at is distance, the position function. So if we start with the first function as position, and that's f of x, okay, what do you think the change in position, what will we call that? Displacement, okay. Displacement's a word that's used in there as position. It is actually used. It does show up on the exam, so. Any ideas? Really? Anybody taking physics here? Yeah? So what's your change in position? Like, for example, if I'm 6 kilometers from my house, yeah, it's speed, velocity. The change in my position is a speed or a velocity. So for us, we're going to be more specific. We'll call it velocity, because if we have positive and negative numbers, we want to interpret that differently. Speed is just, there's no direction associated with speed, right? But velocity we can associate to a direction. So this would be the change in your position is your speed or velocity. So what's the change in your velocity? Okay, so now you're onto the pattern, right? Acceleration is the next one. That describes how much your speed is either increasing or decreasing. So acceleration or deceleration. And that would be the second derivative. So that's usually how we write second derivative. Usually if we're going to go higher than second derivative, it's usually written like this. Like if it was the fourth derivative, they usually just write a number 4. You know, you don't want to do all those tick marks. Eventually it's faster just to write a number. Okay? But for our course, the 99% of the time we'll be interested in these two here, the first and second derivative. So if we're on the moon, there's no atmosphere, which is convenient for physics because that means there's no resistance for wind or air. The position function, if we were to drop something, is given here from 2 meters. So we're not actually interested in finding any specific data, but what I'd like to know is, so this is basically like an astronaut's holding like a golf ball, right? So they're holding it up at about 2 meters, they let it go. So what would the velocity function be on the moon for this golf ball to drop? Really? Yeah? Well, it must be me then. I must be off today. So this represents what? The height represents position. So how do we find the velocity if I know what the height is? It's the derivative, yeah. So that means that's the function for the velocity. You give me a time, I'll tell you how fast that ball is falling. What about acceleration on the moon due to gravity? What's the coefficient there then? What do you think? Like on Earth, it's 9.81 meters per second squared. On the moon, it would be, yeah, so it would be 1.62. How come it's negative? Falling towards the moon, right? So the distance is getting smaller. So anyways, if you check with your physics formulas, those of you who are doing physics right now, you'll notice that there's one function that gives you the position of an object. If you look at the one that gives you the speed, they're just taking derivatives, but they never told you that because you don't have to take calculus before physics, right?